Today's problem is submitted by a viewer, and it says a function s of x returns a minimum positive integer such that its multiplication of digits equals x. If there is no such integer, the value is 0. Find positive integers less than from positive integers less than 100, find an argument a such that s of a is maximized. Interesting. Okay, and then there's a follow-up bonus, which is do the same thing for a larger number. Do it for 10,000 rather than 100. The viewers also said that he's noticed this problem is not easy, and they came to an answer because of a happy accident. Okay, so even just off the top of my head, I'm not really sure exactly where to start. First, let's try and figure out exactly what this thing is asking about. So s of x is equal to y such that the product of the digits of y is equal to x, where so y is equal to the sum values 10 to the I. So I guess I has to start from 0. So it returns an integer such that the product of the digits is equal to x, and it returns the minimum possible integer. Wow. So for when I don't know where to start in questions like this, I often like to think of some specific examples. Still in terms of just figuring out how to how this function works, why don't I just compute s of 1 or s of x for a few values of x. This one is certainly equal to 1. S of 2, I suppose, just equals 2, and this is going to be true for all single digit numbers, right? S of 9 will equal 9. The product of just a single digit 9 is equal to 9. There's no smaller number which will do this. Okay, s of 10. So 10 is equal to 2 times 5. So the smallest number that works here is going to be 25. Right? Okay, 12 can be written in many ways. 12 is equal to, and we have to write this as a product of one-digit numbers. So this is 2 times 2 times 3. It's also equal to 4 times 3. So, 34 seems to probably work. No, that's, no, actually it doesn't. 26 is smaller. I think that's going to be the smallest one. Oh, I made a mistake here. S of 11 is not 11. S of 11 is going to be 0. So again, in the statement of the question, there is no such integer such that its digits will multiply to 11. In fact, I'm tempted to say now, for any prime which is not one digit, the answer is going to be 0. Right? right? Let's take a larger prime. 29 is equal to 1 times 29. But because this is a 2-digit number, right? 2 times 9 is equal to 18. There's no way to get 29 as a product of 1-digit numbers. So in terms of answering this question for positive integers less than 100, so we want to find A to maximize S of A. So we can, and well, we want to find A less than 100 to maximize S of A. Yeah, we can eliminate all the primes, certainly. What might be one possible way of trying to solve this is, come up with a candidate for what S of A is and try and back out what the value of A could possibly be. So, so this is sort of like thinking about what is the range of this function S. S of X can't have a 1 in it. Except for S of 1, right? And the reason why it can't have a 1 digit is suppose S of X is equal to, let's just choose some random number, 149, okay? Well, 1 times 4 times 9 is 36, but 4 times 9 itself is also 36. So because S of X has to be the smallest integer, where the product is, in fact, this 149 is a candidate for S of 36. And 49 is less than 149. So S of 36 certainly has to be less than or equal to 49. Okay, so there can't be a 1 in the digit. It cannot have 2 2's in it, right? Suppose again S of X is something like 223. Well, 2 times 2 times 3 is the same as 4 times 3. So we can't have 2 2's. We also cannot have, I guess, a 2 and a 3. Like, it seems to be that for this number x, we have to look at the prime factorization but then also group these primes in a particular way. So I want to maximize this number. I want to maximize S of X. We probably want a number also, x. X should have a lot of prime factors. If I take like let's experiment. I'm gonna choose a couple arbitrary values of x less than or equal to 100 and just see kind of what happens here. Well, let's compute s of 100 for one thing. So 100 is equal to 2 times 2 times 5 times 5. For obvious reasons, there also can't be a zero digit in s of x. Otherwise, the product of everything is just 0. So is this the smallest integer such that the product of its digits is 100? Probably, right? There's the prime factorization of 100. If I try and collapse any two other things, right? 2 times a 5 is 10, which is longer than 2 digits. Can't really put that into the number. Same with 5 times 5. So I think 455, that's s of 100. Pretty sure. Let me choose some other arbitrary numbers here. S of 48. 48 is equal to 2 times 24, which is 2 times 2 times 12, 2 times 2 times 2 times 2 times 3. So we can do a lot of collapsing here. In particular, I can bring that down to 6 times 8. Right? There's 8, there's 6. And I think that's probably the smallest, because any other, obviously 86 works, but that's larger than 68. There won't be any other 2-digit numbers that work here, I don't think, right? Because we would have to take a factor out of the 6 and put it into the 8, or the other way around, out of the 8 and put it into the 6. So is there another grouping of these things? 2 times 2 times 3. That's longer than 2 digits, so that won't work. So what makes this number big? It's a large number of what about something like s of 99? So 99 is 3 times 3 times 11. Okay, so here we see another thing then, is that if x has a prime factor which is 2 digits or more, then it won't work. So we saw here that primes will always give us a 0, but so will any number with a prime factor greater than or longer than 2 digits. So we have no primes, no x, such that x has, I'll put in quotation marks, a long prime factor. So that rules out all, well, you can figure that out. It rules out a lot of numbers, multiples of 11, 13, 17, so on. I feel like, okay, so look at how we got this. We got a pretty large looking. What if I multiply 4 different primes together? 2 times 3 times 5 times 7. So 6 times 5 times 7, that's 30 times 7, but that's greater than 100. So that doesn't work. Well, we know that we're looking for a number greater than 455. If the first digit is a 5, then the next 2 digits have to be greater than or equal to 5. But 5 times 5 times 5 is 125. Okay, so if it's a 3-digit number, if the thing we're looking for is a 3-digit number, then 455. Oh, wait a minute. Yeah, if I make any of these digits larger, the product will be greater than 100. So it's not going to be a 3-digit number greater than 455. So let's think about 4 potential 4-digit numbers. If it starts with a 2, then the next digit cannot be, it has to be 5 or greater. Because if I put a 2, 3, or 4 here, then I would instantly just combine it with that 2. So 2 times 5. I need to fit 2 more numbers in here, and they have to be greater than or equal to 5. But if I put a 5 and a 5, that's greater than 100. Okay, I think the answer is going to be 100. I think this is going to be the largest one. And let me set out my reasoning. So let's start by assuming that S of x is equal to ABC, where these are the digits of a 3-digit number. So A times B times C is equal to x. Well then, at least one, oh, hold on. No, because I could have 4 times 6 times 3. So that's 12 times 6, which is equal to what, 72? Okay, let's write out the prime factorization of 72. Well, it's 2 times 2 times 2 times 3 times 3. I feel like I wrote this one out already before. No, I wrote it 48. Okay, so for 72, is there a smaller rearrangement here? I think so, right? 89, right? Okay, well, maybe what we can do is, again, start with 455 and modify these digits. So like 4, I want something bigger than 455. 463 did not work. 464. But no, so the digits, yeah, here's another problem with this. The digits have to be in increasing order, right? Because this is not even a candidate, so 463 can be rewritten as 346. Yeah, so 455, if I want a number, the digits have to be increasing. So if the result is greater than 455, yeah, like there's not going to be a 3-digit number. There's not going to be a 3-digit number greater than 455 because then the product of the digits would be greater than 100. So let's look for a 4-digit number. So A is less than or equal to B, less than or equal to C, less than or equal to D. Any product of these numbers has to be greater than 10. In particular, A times B is greater than or equal to 10. And because they increase in this direction, the same will be true for any other product. You know, B times C will also have to be greater than or equal to 10. Okay. So what could this number potentially be? If I want to make it as small as possible, right, that's the way that S of x works. If the first number is a 2, the second one has to be a 5 or greater. But then I could put 5 and 5 here, but that product is greater than 100. So let's start again. The first number is a 3. The next one could be a 4. And the next one could be a 4. And the next one could be a 4. What does this equal? That's greater than 100 again, right? This is 3 times 64. Starting to think the answer really is 455, or so S of x, so x has to be equal to 100. Oh, the question says positive integers less than 100, not less than or equal to 100. Okay. But I think sort of reverse engineering the answer like this might be the way to go. 4 times 4 times 5, this is 80, right? So S of 80 is certainly less than 445. Can I write this in a smaller way though? So this is 2 times 2 times 2 times 2 times 5. I can write this as 285 or 258. So S of 80 is equal to, I believe this is probably the smallest we can get, 258. So let's stick with 3-digit numbers. Let's assume that S of x is a 3-digit number. And try and make this as large as possible. So 4 times 4 times 5 doesn't work because it ends up being not in the range of the function s. So what about 3 times 4 times 4? I don't think this is going to work either, because this is 3 times 2 times 2 times 2 times 2, which is equal to 6 times 8. Okay, so 344 doesn't work. I guess we worked this one out earlier, didn't we? This is 48. Okay, so what about, so 3 times 3 times 3 also doesn't work because this is the same as 3 times 9. And 3 times 3 times 4 won't work because that's 4 times 9. Okay, so the first digit, what about first digits that are larger? What if I have, we've probably worked this out, right? If it starts with a 5, yeah, that can't work. Okay, so the first, if it's a 3-digit number we're looking for, the first digit's going to have to be a 2. Okay, then the next digit has to be a 5 or higher, because otherwise we could combine them into a single digit. What is 2 times 5? Well, I've already got 258 as a potential candidate here. Would 259 work? 2 times 3 times 3 times 5. So in all the possible ways that I can I think 259 will be the smallest arrangement of these, right? If I combine these, that gives me a 6, and the 2 is better than that. I can't combine anything with the 5, because those products are all greater than 10. Multiplying the 3 and 3, that gives me the 9. So, and what is this equal to? 90. So if I want a bigger number here, what about 359? This is 5 times 27. That's greater than 100. So 259. Have I found one that's 258? These, you notice that these are all, 256 and so on. These are all going to be the multiples of 10. I'm somewhat tempted to say that this is the answer. So 90 is the one that gives us, 90 is the number less than 100, which gives us the maximum result of S of x. The bonus question, though, do this for numbers less than 10,000. I don't know if I want to work into that immediately. Maybe I'll save that. I think what I'll do is I'll probably let this problem sort of bake in the back of my mind for a little bit. And then if I have any ideas for elegant ways to approach this, this was some combination of elegance and brute force, probably more on the side of brute force. But I think certainly figuring out digits that can be eliminated in the result, being able to eliminate all 2-digit primes and all multiples of 2-digit primes, that eliminates quite a few options. What else was nice here? Realizing that the integers have to be increasing, or the digits have to be in increasing order, right? So this would be an illegal output, but because you can just replace it with 346. And then from there, I think trying to sort of reverse engineer the maximum possible value that you can get here might be the way to do it. So I don't really know, with all these things put together, if we're looking for the argument less than 10,000, which maximizes this, with all these things together, I don't know how many options I've sort of eliminated, but I think I'm going to leave this one for now. I don't know for sure that this is the answer, but I think it's a pretty good result. Pretty good, I don't want to say guess, but it's not too far off maybe. I'm just going to check quickly the numbers greater than 90. So like, what is S of 91? So 91 is equal to 7 times 13. Okay, so that can't work because of the 13. S of 92. 92 is equal to 2 times 46, which is equal to 2 times 23 times 2. So again, we have a problem because 23 is a 2-digit prime. S of 93. So 93 is equal to 3 times 31. Doesn't work. 94 is equal to 2 times 47. 47 is prime, right? 95 is equal to 5 times 19. 96 is 2 times 48, which is 2 times 24, 2 times 2 times 8 times 3. And this gives us 268. Uh-oh. Shoot. Oh, wait a minute. Wait, no, this is probably right. 268. So certainly less than or equal to this. Let's see if we can figure out another way to rearrange these digits. 2 times 2 okay. 1, 2, 3, 4, 5. Wait. Did I mess something up? Ah, that should be a 3, not a 6. Yeah, so this is 32 times 3. (32 times 3 is 96. So I can write this as, like, if I combine those and combine those, I get 268. I'm sure there's no way of doing this any smaller, right? It would have to be a 2-digit number. Okay, well, good thing I did this check. S of 96 appears to give us something greater. 268 is greater than 259. Can we go a little bit higher? What is 2 times 7 times 7? This is 98, right? Okay. So S of 98 is 277. And we're not going to get anything bigger than that. Yeah, again, what if the first digit is a 3? What went wrong before? Then the next digit has to be at least a 4. And the next digit has to be at least a 4. But this can be rearranged, right? That's the problem, is that this could be turned into 3 times 2 times 8, which is the same as 6 times 8. So what if we have 3 times 4 times 5? So 2 times 2 times 3 times 5. Yeah, this gives us 256. Right, the 3 and 4 is the problem, right? Because 3 times 4 is the same as 2 times 6. So if there's a 3 and then a 4, that's going to be illegal because that can be replaced with a 2 times 6. So 3 times 5 times 5. That's 75, right? And what about 356? I don't think this is going to work because this is the same as 3 times 5 times 2 times 3, which is the same as 2 times 5 times 9. This is turning into really brute force, but I am at least being somewhat reasonable in trying to construct the answer. So if I put something that's a multiple of 2 here, if I put an 8, this is still, oh, but this product is now greater than 100, right? This is equal to 3 times 40. Okay, what about 357? I think we did this one already. This is 21 times 5 greater than 100. So maybe this is the answer. Okay, hold on. What about 4 times 4 times 4? No, because that's the same as 8 times 8. Yeah, I mean, at this point, I may as well just compute every single one of these numbers, but 355. Yeah, if I come back to this to continue with the 10,000 one, looking for the largest argument less than 10,000, which works, I'm going to start with trying to directly construct the number on the right-hand side. The largest possible number on the right-hand side, which is legal, which could be an output of this. I'm gonna stop here though. I've been working on this pretty long, and I keep changing my answer. But yeah, I hope this is correct. I suppose I could write some code to check this. Maybe I'll do that at some point in my free time. But this is what I'll say finally. This is a really cool problem. I think there's probably some kind of, I wonder if there's like an algorithm that you can use to sort of, I don't know if algorithm's the right word, but some way of like I suppose there's got to be some kind of algorithm to like if you fix the number of digits in the output. So in this case, we have 3 digits. Fixing the number of digits, trying to construct the largest possible number, which is allowable there. Like the sort of things that can go wrong is, of course, you might write down a number, but that can be rearranged into something else where the product of the digits is the same. So the algorithm would have to take care of being careful with that kind of thing. But it seems like there's a lot to do with basically powers of 2 and powers of 3 that go into this thing, because those are the ones, it's powers of 2 and powers of 3, or 2 times 3. These are all ways that you can rearrange the digits to still have, you know, the products of those things that are less than 2 digits long. Yeah, this is a cool problem. And I'm going to think about it in the back of my head, and then I think I will come back to this bonus with 10,000. But anyway, it's been a long one, a lot of rambling. I hope this is the right answer. Thanks for watching.